But now let's get to the main course of the webinar, which is the actual algorithm called reversed concept drift. What can we use it for? So we can use it to do two things. We can either estimate the magnitude of the change in the concept, or we can estimate what is the actual impact of this concept change on the performance of our model that we have deployed to production. So to give you an example of how concept drift actually looks like, imagine that we have our familiar feature X here, and what we're trying to predict is feature Y, but to be more specific here, the feature Y is binary, of course, and we are trying to, apart from just being good at predicting it, we also want to actually correctly predict the probability that feature Y is 1. And we've seen that beforehand, the original concept that we trained our model on was this kind of sigmoid curve, which was centered around, I would say, 0.0, so exactly in the middle here. And in time, this curve, for one reason or another, has shifted to the right, and now we will see that the ideal prediction for, let's say, value 0.5 used to be almost 1. Almost all the data points were already positive class, whereas now almost all data points for prediction for input feature equals to 2.5 is going to be 0 or close to 0. So we see that the model will really badly mispredict on any features or any model inputs that are sampled from that region where the concept has changed. And we are trying to, first of all, somehow quantify how big that change is, and secondly, quantify the impact of that change on the expected performance of the model. How can we do it? So first, we need to assume a couple of things. First of all, we're going to assume that there's no covariance shift. Later on, we're going to be able to slightly relax this assumption, but the way we're going to be looking at the result is always with the assumption that there is no covariance shift, even though the algorithm will work perfectly fine, even with presence of certain types of covariance shift. Then the second assumption is that we're going to be looking at specific batches or chunks of data that we're going to try to evaluate whether there is some concept drift or not. So imagine that you deploy your model and you want to, for every day, measure whether there's concept drift or whether there's no concept drift. This is our chunk, so we can chunk our data daily. If we don't care about any specific time period, we can also just say that for every, let's say, 10,000 new data points that comes in, I'm going to batch those 10,000 data points, and I'm going to measure whether there is whether there is a change in concept of that 10,000 data points compared to my reference data, which, for example, can be the test data. So as we look at our monitor data, the data that we monitor, we're going to split the data into chunks. And this chunk size needs to be big enough so we can actually learn the concept that exists on that chunk of data. In practice, it means that basically we need around at least 1,000 data points for every chunk of data. So if, let's say, you only get 10 new predictions every day, you might want to not chunk your data daily, but instead of doing, let's say, monthly. So then at least you'll get a tiny bit more data to actually create those chunks. Then the last prediction, which is kind of a the last assumption, which is kind of an obvious assumption, is that the algorithm needs to be able to learn a new concept. We use for our algorithm, we generally use gradient boosting methods, which are quite good at learning any concepts. So as long as we're dealing with tabular data, this assumption is basically always satisfied. Even if we're dealing with non-tabular data, sometimes gradient boosting models are good enough. I'm just not going to say that they're good or they're the best, but they are good enough to actually still model the concept reasonably well. Now, how does the algorithm actually work step by step? So what we're going to do is actually quite simple. We're going to train a model on the current batch, or actually, to be more precise here, I have issues with naming, as you can see. We're going to train a model on our current chunk of data. And this is a new model that we're going to train automatically a gradient boosting model on the current chunk of data we have. Then we're going to use that model to make predictions on our reference data, which, for example, can be the test set, but I'm going to again rename it to reference data, just to be fully correct, because our reference data doesn't have to be the test set. It can be, for example, first few months of production. And then we can do two things. We can either estimate the magnitude or estimate the performance impact. Let's first go into estimating the magnitude, but before we go there, I'm going to build slightly more intuition about how we actually train these models and what we do with that model in a slightly more graphical way. So what we're going to do is basically we're going to compare the two models. We're going to compare the two models to actually compare two concepts, and then we're going to measure the difference between those concepts, because the underlying assumption is that the model accurately captures the existing concept in the data, so existing pattern that we're trying to learn, that the model succeeds at that task. So we're going to take our model that we trained on our training data, and we're going to make some predictions on our reference data. So again, let's say most of the time it's going to be the tests. Then we're going to take a new model that we trained on the last chunk of data or a chunk of data, and we're going to also use that model to make predictions on the same data, on the reference data. So we're always going to be using the reference data to make the predictions on. And then we're going to compare those predictions. So we're going to compare the predictions that we get on the test set or reference set from the model that we trained on our training data and from the model that we got on our current chunk. And if these predictions are similar, we're going to say that there is no concept drift. If they are different enough, we can then talk about the existence of concept drift, and we can then quantify how strong it is. And then the notion of similar or different, of course, needs to be quantified. So I'm going to, in a second, explain how we actually can do it. Let me just give you one final piece of intuition of how it actually works in a kind of real-life production setting. So the way we do it, of course, is we're going to make these comparisons, but we're going to do it step by step. So for every chunk of data, these chunks actually would be just single data points here. I made them slightly larger just to make the visualization easier. But for every of these data points here, we're going to train a new model. We're going to make predictions on reference data. We're going to compare those predictions with the predictions that we got from the original monitored model. And then we're going to measure, for example, the difference in the F-score we get based on these predictions. And we're going to plot those over time. And if we see that the predictions are getting worse, it means that the concept is changing. And that is kind of the example in the nutshell, the final piece of intuition of how the algorithms work. It's really not that complex. What is interesting, though, is, of course, how exactly we can quantify the similarity or difference in predictions. How does it look like? And then in a second, I'm going to talk about the limitation and why it's so useful. So we see that if we look at the magnitude estimation that I already showed, it goes up in time. And just looking at the screenshot from our cloud product, we see that F1 delta, so change in F1 due to change in the concept. We see that it's also dropping. We also have some kind of confidence bands here that tell us whether we should trust our predictions or not, which are based on the size of the sample. So even if you cannot get to this 1,000 data points per chunk, you will still be able to get some information, and you will know how strongly trust your predictions, because we have these confidence bands. I can talk about the confidence bands later on if there's questions about it. But now we see that as the magnitude of the concept drift increases, we see expected drop in performance, because if there's concept drift, generally performance will drop. But if you look closely here, it doesn't really follow one-to-one. So we cannot just use magnitude estimation as kind of the only metric we want. If we're interested in change to F1, we actually need to look at the performance impact estimation on F1. Because if you look specifically here, you would say that there is very strong concept drift, but the performance is kind of recovering. It hasn't dropped very strongly for that specific chunk. And then you can actually use that, because if you look at this data point here, if you train the model, what you would expect is that the impact of concept drift will kind of disappear. So you stand to gain around 0.07 F1 from retraining, which is very useful, because then you know whether it makes sense, or whether it's worth the candle to actually train your model, or whether the drop is small enough that retraining might not be warranted, because retraining might be expensive. It might require a lot of cloud resources. It might require a lot of paperwork, bureaucracy, etc. So that gives you an actionable information of whether you should retrain your model or not.